Hey folks, in this video we're going to take a look at another way to analyze snippets of code. Our goal is to be able to find something that looks like big O, or maybe even tilde, or maybe even a growth function. So I have a bunch of for loops here. So what I'm going to do is I'm going to take the approach of trying to understand the different values that I can take on as that loop unrolls, right? So as it occurs, as it prints something in our example. So I'll get more to this in a second, but let's just start with our cost metric. So what we're going to try to analyze here is the number of calls to println. So let's just jump in and see what this looks like. So in my first snippet of code, I have basically my int I equals 0, I less than n, and I plus plus. So this bit of code right over here. We already know, right, the different kind of parts, right, and we know what those mean, but what does this mean in terms of that value of I? So let's just take a look. So if I think about this, I is initially going to look at something like 0, right, and then I'll go to 1, and then 2, 3, 4, 5, right? It'll just keep on going up like that, right? One at a time. That's what I got from my I++ over here. And it starts at 0, and obviously it's going to go until just under n, right? So it keeps on walking up, and so it looks something a little bit like this, right? And then it goes up until, approximately n. Okay, so this is the sequence of values that I takes on. Now, for each of these, println is going to basically go off once, right? So this is actually telling me a little bit about how many times this loop runs, right? So this loop runs, right, n times. And I can see that from the sequence here, right? I'm counting up, going from 0 to n times. So this is the simplest thing I could have, right? And so if I have a bit of code like this, this becomes big O of n. Okay, so not too surprising there. But also I can say that it's basically tilde of n as well, right? Okay, hopefully that's clear. That's kind of our simplest case. Now it's going to get a little bit trickier. So let's take a quick look at the next loop. Now the bit that's changed here is the last part, how I updates, right? So now I have I plus equal to. So let's see, what does that do? And again, my goal, right, is to be able to figure out what the performance is of this, right? So I'm going to trace the sequence, try to figure out basically how large it is, and that tells me the performance, right? And actually, let me add an annotation over here. So if I think about this over here, right, the values of n, or the values of I, excuse me, that were seen in the previous loop, I kind of realized that happened n number of times, right? Hence my performance. So let's try that same idea, though, on this other example. So in this case, right, I'm going to start with 0, right? I'm still starting at the same place. But then what happens is I go to 2. And then 4, and then 6, and then 8, and I'll just do little ellipses here, dot, 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 all the way up to n, right? I have the same ending point, right? And so now if I think about this, right, I'm going every other position, right? So I'm not going to go n times, right? This loop doesn't run n times. It's skipping every other position. Really, it's going to run n over 2 number of times. So actually, if I think about this, the number of times this happens is this over here. And from that then, right, so that's the exact number of times it runs, then I can figure out my big O and my tilde. And for my big O, right, I kind of know that big O doesn't have factors in there, right, that gets removed. So this is really just big O of n. Now if I had tilde, I would keep it, right? So I would say this is 1/2 n, right? And so we're able, right, we're able to basically figure out what the performance of this thing by looking at that sequence of values that is visited while the thing loops. Let's try another case here. So now I have I equal 100, right? So I'm going to change the starting position. So in that case, again, I draw out my sequence. So I start with 100, 101, 102, 103, dot, 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 up until n, right? I have the same ending place, right? And so now I just have to ask myself, how many times does this happen? Well, if I think about it, it's going to basically happen n minus 100 times, right? So this is really n minus 100. What I'm drawing here, right, is something akin to almost to the growth function when I'm doing this little annotation above. I might be off by 1 or 2, but it's effectively an exact value. The offness would come from the fact that usually we increment I one more time than we check the conditional, because we need to fail as well. Okay, but anyway, so let's try to figure out the big O for this. N minus 1, that's just going to be O of n, okay? Now, if I was doing tilde, this would actually become tilde of n as well. Tilde doesn't use that like least dominant term, right? So it only uses the dominant term. If there's anything less, right, it doesn't use that. So the fact that there's a negative 100 kind of disappears in tilde. Okay, so hopefully that kind of makes sense. Again, we're just tracing out the sequence. We want to see what values are visited, and then from that, we're going to kind of figuring out, how many times does it run. Let's do a few more. I'm going to do a little bit trickier now. So let's take a look at something with a multiplication, right? So the part that's different is the end part, right? How I change my variable. So in this case, right, again, I'm going to start writing out my sequence, and notice starting at 1 so that I don't get any multiply by 0 things. So I go to 1, 2, 4, 8, 16, right? So I'm doubling, right? Dot, 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 all the way up until n. So this is definitely a different sequence, right? And one thing I'm going to really point out here is that in these examples, as we move forward, we are moving essentially a constant amount each time, right? So +1 each time or +2 each time. It's a constant amount, right? So it's not like I change the pace that I move towards my endpoint. It's always the same. Versus over here, I have this example here where basically I'm getting larger by a factor of 2 every single time. It's a different kind of feeling, if you would, of progression, right? I'm increasing at an increasing rate. Okay, so what do I do now? Well, basically what I have to do is I have to ask myself, how many times do I need to double 2 until I get up to a value of n? Now, this is, you can think about this for a second if you want. There's actually a math that can get us there really easy. Well, turns out it's a log. So actually, if I use a log base 2, that tells me that power I had to put on 2, right, all the way to get to that value, right? And so that actually is going to give me the number of values that I see here for I, right? So this whole sequence here becomes log base 2 of n. Okay, there we go. And that base 2 is coming from this over here, right? So because I move up my multiplier right by 2, it's giving me this kind of 2 power structure, right? So log base 2 of n is the size of that sequence, or the length of that sequence. And so now if I want to do my big O, it's pretty simple, right? This becomes log n, right? And since it's big O, I don't really have to bother, right, with a sub on it. And I could also say, right, this is tilde, right? Now if it was tilde, then I would be more specific. I would say this is log based, well, not log based n, it's supposed to be a log based 2. I don't know why I keep on thinking it that way. Log base 2 of n. There we go. And the base difference, right, is just because in big O, right, we don't really care, right? It's a constant factor, so it doesn't do anything for us. So yeah, we get some more log base terms. Let's do the other one here. So let's go this here. We start at n, and then we go down. So I'm just going to arbitrarily pick, like, let's just start at some real number. Let's start at 64, right? So if I start at 64, right, then I half by each time, right? So 32, 16, 8, 4, 2, 1, right? So again, I have the sequence. Notice that basically I'm going backwards from the one up top, right? So actually, this length of this sequence in the bottom is the same as the one on top, right? Because I'm changing in this kind of methodical way, right? I'm doubling each time or I'm halving each time. So you can see those terms kind of just map across, right? So this 1, right, goes over here. This 2 goes over here, right? 4 goes over here. 8 goes over here, right? So it just directly maps across. So it's the same sequence size. So if I wanted to write it, what I would basically conclude is that the length of this happens to be log base 2 of n as well. It's just that they're seen in the opposite direction. And of course, right, really it goes up to some n over here, right? But I didn't really want to include that. And so we get basically the same result, right? So this is going to be our log n for a big O, and our tilde of log base 2 for n. So let's take a look at the bottom part of the slide here. So we have another problem. This one's a little bit more complicated. I would suggest that you start by trying to figure it out yourself, right? So the rules we talked about kind of apply here. And also the other thing I'll add is that if you have nested loops, the way you analyze them is by multiplying them together, right? So you will analyze the first one, then the bottom one, multiply them together, that's your final answer. So take a minute and just try seeing if you can figure out what is the big O from this. And if you want, you can try for the tilde as well. And then I'll work through it and we'll kind of see together what the answer is. Okay, so let's go ahead and give this a go. So my first loop goes from 1 to n and multiplies by 3. So let's see, how does that look? Well, I start at 1, I go to 3, I go to 9, go to 27, ... all the way up to n, right? So we're following the same process we had before. And so what I want to do is I want to figure out how many entries there are kind of in this sequence of values of I. So look at this. I'm going for 3 each time, and I'm increasing at an increasing rate. It sounds like a log. It's going to be log base 3. So actually, the size of this thing is log sub 3 of n, right? That's how many times the outer loop runs. So I feel pretty good about that. Let's take a look at the inner loop. So j equal 100 is okay. So let's see. I have a different starting point. So I'm going to start at 100. I'm going to move up by 5 each time. So 105, 110, 115, ... up until n. Let me think about how many values are there. So it's n moving by 5 each time. Okay, so 1/5 n, and then it starts at 100 minus 100. There we go. And so if I want this whole thing, right, I could multiply this together. In terms of big O, I am going to get n log n, right? So the bottom part is n, right? I don't care about anything that's lower down going terms, right? I could, if I want, right, basically multiply these together, right? But I can kind of get a sense that anything with 100 in there, right, is not going to be as fast growing as the log or the linear factor, right? So the linear factor is what counts. So I have n times log n, right? So this becomes O of n log n. No base on the log because we're doing big O. I could also look at this in terms of tilde. So for tilde, this is going to look like log base 3 of n times, I don't have much space here, but we'll try this, 1/5 n minus 100, right? So that's the tilde of this. And so if you want, right, you could multiply them together, right, and you'll get, a 1/2 n log n factor, and then a minus 100 log n factor as well. But I'm just going to leave them factors as they are. So you can kind of see, right, how this process goes, right? We analyze each of the loops, right? We figure out what they are using a sequence approach, and we multiply them together. That gets us the entire thing, and we can even get at this pretty exact tilde approximation for it. The last note I have here before I go is that this technique only works if your loops have no interdependencies. And so, for example, I look at J doesn't depend on I, right? I doesn't depend on J. Because they're not interdependent, I can analyze them separately and then multiply them. If there is a dependency, only to do something a little bit more tricky, maybe something like the sigma form approach, which we'll be talking about a little bit later. Thanks for watching. I will see you guys later on.